Okay, here's a brief recap over what we did last night. So from what we did, we say generally, a sinusoid waveform is going to be represented in the form Vmax, and then you have cosine omega t plus some phase angle phi. So this is the standard format that we're going to use. And then we did see to say that this being standard, every now and then you have questions where instead of giving you a signal or an excitation, by excitation it can be a current supply or a voltage supply, instead of giving it to you in form of a cosine function, it's possible you can be given something, let's say this, and then you have, I think among the examples we did, you can even say 10 here, then you have maybe sine, you can even say 8t. Now we start to say it's possible for us to transform this from a sine function so that we express it in terms of cos and so on. For the most part, we start to say the approach is the double angle identity for cosine that we ended up using. Now, I didn't want to give you guys to say that you're just going to memorize and use plus this or minus that, because I want you guys to be flexible. So that should you find a question, rare of course, where what you actually need is the part for changing maybe cos to sine, you'd still be able to do it. But the most common thing that you actually work with here is where you are changing the sine to a cosine, because standard is going to be for cosine. Okay. So we saw how those changes occur. Then one other question that you guys mentioned was the use of omega t plus 90 degrees and the use of omega t minus 90 degrees as the argument for cosine or sine. Now, what you have to get is that the times when we get to use minus 90, this happens because if you were to look at a scale like this, and then I ask you to measure positive 270. Positive 270 will be an angle measured from here coming up to this point. This is the positive 270 measured anti-clockwise, which is the positive way. But you have to understand that if this is phi here, which is equals to positive 270, we can actually achieve the same result by going the other way in this way until when we reach that point. Notice that we still describe the same vector, but the difference is that now we're using phi is equals to minus, and we have to move 90 degrees. But otherwise, we still describe the same thing. This is the reason why, for cases where you have to write omega t plus 270, notice that the same thing can be represented as omega t minus 90. These two will actually mean the same thing. I hope you guys get this. I think this is in line with the question that Zamila asked towards the very end. I think I did answer her, but I thought I just mentioned it as well as we started. In tonight's class, however, we now want to focus our attention on the phasor representation of some of these. We start to start by looking first at what the phasor is, and then after that we're going to move on to look at circuit components like the resistor, inductor, and capacitor, and look at how we describe what is happening to them in terms of this phasor notation. Largely in last night's class, we basically just looked at the sinusoidal waveform and how to move from one form to another. But everything we did is what you guys will need when it comes to AC theory. So you'll see how the whole thing relates. But first, we introduce the phasor. Now, what is a phasor? I think we didn't do the phasor, but to just avoid repeating myself. Okay, looks like we did not. What is a phasor? Well, a phasor is just a complex number representation. So it's a way of representing a supply or quantities like voltage or current, but want to represent them in terms of a complex way, as a complex number. Now, the complex number that we want to deal with is going to store only two important details about the signal or about the supply we're dealing with. That is, it only stores the maximum value. If you're dealing with a voltage supply, then that complex number will only store the maximum voltage, and it will also only keep the phase angle. If you're dealing with current supply, then the phasor notation or the complex number we want to use here only stores the maximum current and also the phase angle. So these are just the two things which are actually very important when it comes to describing what we are actually supplying: the shift, which is the phase angle, and the maximum, which is available to us. Now, to understand that, we first look at complex number just in general. Let's say you're dealing with a complex number, and Z here is said to be a complex number. Complex numbers, we know to say they have two parts. The real part, I'll say X is the real part. And then the imaginary part, I'll take Y as the imaginary part. We have this here. So in this case, of course, we're saying that we have something like this, where this is the imaginary part, and this is the real part, RE. So if this is our complex number Z, then you have to see the two parts are going to be this and this. This is X, this is Y, and let's take the resultant here to be R. I'll try by all means to skip the derivations, or at least move through them very quickly, so that we only stick to what is very, very important when it comes to AC. But I think for these bits and bits, I might still go through the derivations, because understanding them really just helps you guys get a full foundation or full picture of what is happening, even when we start looking at the actual circuits themselves, because they'll largely be dependent on what we're doing here. So this is what you have here. So clearly from here, this way of writing a complex number, this of course is the Cartesian form. But of course, there are three forms or three versions that you have to understand when it comes to representing these. The other two involve the polar form, which is writing the complex number Z as its magnitude and then the phase angle. The phase angle, of course, on the diagram is represented. And the last part is in terms of the exponent form, which is R, the magnitude, and then E, and then you have the unit vector, not the unit vector, the complex variable J, and then the phase angle phi. Now, of course, you should be able to move from one form to another, depending on what you are given. We'll see examples and perhaps relate it all. But then, suppose you have a supply, VT, and this VT is a voltage supply. You have Vmax here, and then you have cos omega t, and then let's say you have plus some phase angle phi here. What happens in this case? Well, you can actually transform this. You see, what you're given here, it's a time-varying voltage supply. So in terms of how we view this, you want to look at this as the time domain. So this will be described as the voltage, but given in the time domain. An example I like giving in terms of these domains is the expressions are basically the same thing, but one is viewed in terms of just a different reference frame. I'll describe that a little bit later when we actually get to compare the phasor and the actual voltage that we're describing. But if this is the actual voltage that we are supplying, given as a sinusoidal waveform, meaning cosine and so on, in phasor notation now, remember I said the phasor will only store the peak voltage and the shift related. In this case, the phasor voltage V, now you have to understand here to say the phasor voltage and the voltage supplied here are different, but they do share a few resemblances. But to show that they're different, we'll put a bar there to say this is voltage, yes, but it is not the actual voltage. This is the phasor voltage. So to present this as a phasor, all we need is the peak voltage. And if you recall, the peak voltage is going to be given by whatever is here, the coefficient of the cosine there. So if what you have here is sine, of course, we have to transform this. So in this case, this is going to be the peak, which is Vm, and then the phase angle. In this case, the phase angle is phi there. So this is what is going to be the phasor voltage, written, of course, in polar form. Now, this, of course, now I'm saying this is in the frequency domain. This is now in the frequency domain. Now, when it comes to these domains, one example I like giving to just help you guys picture the difference perhaps between the two is that imagine what usually we say when it comes to church and so on, where you find a pastor who says that I was in the spirit. Of course, I don't say that. We have someone who say that I was in the spirit, and then you have also the flesh. Picture this to be the flesh, and then picture this to be the spirit. Basically the same thing, but just looking at it from different points of view. So of course, I don't know if that helps you to just understand that these are two, these things are the same, but they're different. So yeah, basically that is that. I'll show you exactly when we switch from the time domain to the frequency domain. I'll keep talking about that whenever it pops up. Consider an example like this. You have Vt, and Vt here is given as 12. And then you have, let's say, cosine, and then you have 5t plus, let's say, 30 degrees. The first example is always the easiest, and then I'll keep complicating as we go. So from here, of course, if I wanted to write this in polar form, if we wanted to present this in polar form, of course, we know to say this is going to be very basic. What we're going to have here is in polar form. Now I'll write V phasor. This is the phasor voltage, and this is going to be given as the peak voltage. That is going to be 12 volts. And then from here, all we need is the phase angle. You know, the phase angle is that. So we're going to have the 30 degrees there. So we have represented the supply voltage in phasor form. So that is all we have to get from that. Now, other examples that we can look at here is, say you have something like a supply voltage. Let's go to current so that you guys know to say it's not only voltage that you play with here. Can be current. Say you have current here, and let's say instead of the usual, let's say you're given something like sine, and let's say you have 5t. So express this in phasor form and let's say polar version. What would be the first thing that you'd want to do here? What do you guys think? Okay. So yes, just as you pointed out, the first thing that you'd have to do here is transform this from a sine to a cosine. And I think we saw how this goes. All we're going to have here, of course, this is positive. So this is going to be 150. And this will have to be cos. Do you guys remember how we transformed this? So it's going to be cos what? 5t. What do we have here? Do you want to have plus or you want to have minus? Which one do you want to use here? So you can use plus 270. It works. Or you can say 5t minus 90. Why does it work? Let's start with the 270. If you just focus on this part, you should see that it reduces to just give you sine. This part is going to reduce to give you sine 5t. If you're not sure, you can still play around with this and see that it actually happens like this. From the double angle identity for cos, you're going to have cos 5t, then cos 270. Cos 270 is 0, making the first term as 0. The second term is what survives really, but it starts with a minus to be minus sine 5t, but the second part will be sine 270. Sine 270 is -1, and this -1 is what comes to oppose this, making it a positive, so that this reduces to just 150, and then sine 5t. So clearly you can tell that it's 270 that works. Even minus 90 works, but if you're using minus 90, then what you're going to have here is minus 90. If you decide to go with minus 90 here, then what you're going to have is minus 90 here. And of course, sine being an odd function, sine minus 90 is the same as negative sine 90, meaning the negative will come to make this a positive again. And then you'll have sine 5t, sine positive 90 now again comes to give us 1, leaving us with only that again. This is why sine 90 and as 90, negative 90 and plus 270 work. But I'll stick to 270 there. So we're taking our phi to be positive 270. If we go with positive 270, it implies that we have now transformed our supply current so that now it comes out in terms of cosine. Having done that, now if we wanted to write it in phasor form, polar of course, you can now observe that the maximum supply current, IM, is basically just 150. And this is current. In most cases, they'll give you the units. So we'll say this is in amps. So this is going to be in amps here. And then next is going to be the phase angle. The phase angle becomes this. In this case, the phase angle is 270. So you have 270 degrees. Again, you could have had negative 90 degrees. So that from here, we can now write this in phasor form. So this is going to be I phasor, the phasor current. This is going to be the maximum current, which is 150 amps. And then the phase angle, 270 degrees. And of course, it is a phasor current, but it is still current. So the units are still the amps. So this is basically what you have there. Any questions? So these are basic questions that I'm really giving you guys, but it's rare that they will actually ask you a question like the way I am phrasing these. But instead, when these questions show up in a test or in an exam, this is how they show up. They show up as part of something more massive. Yes, Michael, you have your hand up. Michael, can't hear you. Okay, we didn't get you, Michael. Okay. Right, so look at how they show up. Look at this question. The question, of course, says for the AC circuit in the figure, use mesh analysis to determine I/O. Mesh analysis is something that you guys already know. The only thing that I think we haven't covered so far in terms of revision is the treatment of the inductors and capacitors. We're getting to those. But for those, I think, who were there for the other time, the other example we started looking at, we did see how we approach those. But looking at what we have done so far, all I want you guys to see is the treatment of this supply and the treatment of this supply. You see, for AC, we don't want to work with that sinusoidal waveform. So the first step would be to transform the circuit from the time domain to the frequency domain. And that will involve changing the supplies from simple harmonic oscillators into phasor notation. This is a voltage supply. So the first thing you'd have to do is change that voltage supply to a phasor voltage. So currently, this is how it is given. You have 10 cos 2t in volts. So how will you write it as a phasor? So what will be V phasor equal to? How do you present this? How would this voltage appear? Can you try this? Anyone to try it? Yeah.
Only 0, I don't know.
What's that?
The angle is what I'm not sure of.
The angle is what he's not sure of. 0. So yeah, you were not. I think you did. You did have an idea of what it was, but you just were not sure of it. So ideally, this is supposed to be plus phi, and it is the phi that comes here. But the fact that there's nothing here, it implies that you are adding 0 to this. So this is what you have. So in other words, the phase angle is actually 0 in this case. So what you have here is 0. Have you got that?
Yes, I am.
Okay. Now, how about this one here? For this one here, what we have is Vt. And this time we have 6 sine 2t volts. So for this one, how do you reckon this will become V phasor? We can even distinguish this by writing this is V phasor 1 and this is V phasor 2. So how would this become now? Yeah. Angle is negative 90. So the treatment of this, I'm sure that she used just a shortcut based on the previous question that we were from looking at. In the previous one, what we had was sine 5t, and the angle phi ended up being either 270 or negative 90. So based on that, obviously this one, which has the same shape, the only difference being the 2t here and perhaps the 6 here, will perhaps be shifted by the same angle, which is 270 or negative 90. So by using that shortcut, she was able to predict this without going through all the math. So this is going to be the phasor form of this expression. Are we okay there? Okay. I'm guessing we are fine up to this point. So having described that, then we now understand what a phasor is. Perhaps the only thing that I would still want you guys to try to picture is how we shift from one form of a phasor to another, and perhaps also the algebra involved with phasor representation. After we are cool with that, then we're going to move on to look at the circuit elements and how we actually approach them. Okay, but to actually perform these evaluations, we're going to look at 2 basic examples, and these examples are going to summarize everything that I just went through now. So let's let Nisa in. Okay. Let's check out phasor algebra. Okay, this is just some math to do with phasors. Suppose you have 12, and then you have a 45 degrees here, and then this is being divided by, you have J and the 60 here, and then this is multiplying 0.1. So say this is what you have. This is going to be our first example. Well, for this one is pretty much straightforward. The bottom is quite obvious. You have 12, and then this is 45 degrees. This can easily multiply. And when they multiply, you're going to have J, and this becomes a 6 here. Now, look at what we have here. The top part is a phasor, but that phasor is in polar form. But look at that denominator. The denominator is also a phasor. The denominator is also a phasor, but this phasor is in complex form. You can't combine them. The only way you can combine them is if you can write the one in form of the other. Well, the easiest way to actually evaluate this is to represent the one which is in complex form. Write it also in polar. It will be easier. Now, how do we do that? Well, in this case, let's focus on that denominator where we have J6. How do we write J6 in polar form? Well, to write it in polar form, all we need is two things. We need the max. These are in terms of what? Doesn't matter what we're dealing with, even if you don't know whether it's voltage or current. All we need is the max. I will assume, let me just look at where I picked this example, because it's part of a different question which has everything else in place. Okay, so I think these are voltages, but doesn't really matter. All I need is I max. So I'll just label this as V max. We just need a maximum value there and also a phase angle phi. So these are the two details that we need. And if we can get from this single detail, from this only detail, want to determine these two information, or these two pieces of information. But how do we get them? See, in this case, the first thing that we want to understand here is that even though we only have J6 here, as a complex number, it must have had two parts, but one part has just somehow disappeared. For it to disappear, it means that one part is actually 0. So this must be 0 plus J with the 6 here. This has to be the original expression, because this is the complex representation of something. Now, what does this mean? Well, for this to be 0, it implies that the x part, the real part, is a 0. And if you come back to, I think I did write that earlier on. See, the real part is controlled by what? If this is the complex variable or complex number, z, that we described earlier on, then the phase angle here is phi. See, the x component, which is the real part, is going to be this side. And we saw earlier, I think I didn't show it here, but I showed it sometime. I can still show it. If this is where we have that V max, you should understand that V max, Vm, this side at the bottom, the x component will be given by V max, and then would have cos the phase angle phi. This is what gives us the x component x, or the real part x. So this thing that should be in this position, it's actually given by V max cos phi. But if x is actually equals to 0, what it means that this V max cos phi must somehow be equals to 0. Wenge, you have a question? Okay. So for this to be equals to 0, you have to see that V max here cannot be 0, because we're saying we're supplying this circuit with something. So it only makes sense that then probably it has to be cos phi, which has to be equals to 0. When does cos give us 0? Cos will give us 0 when the angle is either 90 degrees or when the angle is 270 degrees. So these are the two circumstances where cos will give us 0. That is, if we're dealing with a range from 0 up to 360. So be careful with the range. If the range is said to be from negative 90 less or equal to phi, less or equal to positive 90, you have to see that it actually excludes phi from ever being positive 270, meaning that the two possible solutions where cos is actually 0 now becomes 90 and minus 90. So just take note of what the range is that you're working with. Because if the range is this one, then 270 is not even an option. It has to be negative 90 and 270. And we have seen that negative 90 is actually the same as 270. Okay, so with that in mind, for this part, of course, we're going to go with phi being 90. If phi is 90, then having figured out what phi is, we can move on to look at the second detail that we needed. So we saw, remember, don't forget the goal. The goal is to find a way of rewriting the complex value 6j or j6, changing it from rectangular form and presenting it as a polar form. And in polar form, we needed two things. We needed the V max here and the phase angle. We have just determined the phase angle to be 90 degrees. So we have obtained the phase angle to be 90 degrees. But will 90 actually work? Or maybe it was it was the negative 90 we're supposed to use. To understand whether it is 90 or negative 90, to just be sure, we come back to this part here. The second part. You see, the imaginary part has to be 6j or j6. But how do you get this imaginary part? See, to get the imaginary part, I'll write it as y. Y here, we can clearly tell that y here is 6 according to this. But to find y, we usually say it's the maximum. Then we have sine the phase angle phi. Of course, you can see that clearly by looking at the y component to be this side. It will be the hypotenuse v max, and then sine the phase angle there. Okay, so let me just wait for the recording to catch up. Okay, yes. So this is what y will, how we'll get what y is. So, but according to this part, the imaginary part is actually just 6, implying that Vm sine phi must be equals to 6. Have a question?
Yeah, I wanted to ask, could you please repeat on how you got the y, your screen first?
Okay. So for the y, here's what we did. Firstly, we did observe that the complex number is just this, but we sought to say it has to be 0 plus this. But the components, based on the Cartesian version, something like this, we know to say the resultant or the complex number itself is here. So this is the complex number. But to get a complex number, we look at two things. The x component, which is this one, and this x component, we saw that if I label this as x, this x is given by, let me take to be the magnitude as Vm. So this one will be given by Vm, and then it will be cos the phase angle phi, with the phase angle being this one here. So having done that, the next part is the y component. The y component is this side, and we sought to say the y component will be given by Vm, and then this will be sine phi. So of course, you see, this is just opposite, and the hypotenuse is Vm. This is what is going to be the y. And we know a complex number as x plus jy. So this is how we write a complex number. So here we then see that x has to be equals to 0, and y has to be equals to 6. But y is given by Vm sine phi. So this is how we concluded that y here has to be 6, but y is also equals to Vm sine phi. Are we okay now, Daka?
Yes, sir.
Okay. But from the earlier description, which is the real part, we did see that phi is 90. So since phi is 90, we bring it here. Then 6 is equals to Vm. This has to be sine 90, because where there's phi, we'll now put 90 degrees. Sine 90 degrees is 1. So this part now reduces to just 1, so that clearly now we can see that Vm is actually just equals to 6. So now we conclude that our Vm is actually just 6. And since this is a voltage, I can take it as volts. If you're not sure whether it's voltage or not, you can still just take as your Vm to just be 6. Because above all, in this expression, all you need is Vm, even without the unit. When you're sure of what this complex number is actually talking about, whether it is current or voltage, you can then include the units respectively. If it is voltage, I can then put the volt there. In conclusion, that J6, we have seen that in phasor form, polar, it can be written as the maximum, which is 6, which is Vm, and the phase angle is 90 degrees. What does this mean for the expression that we're actually looking at? We were looking at this expression here. We reduced it first step and wrote it in that form. Now, having simplified the denominator to polar as well, we can now come back to this. where we have this J6, we can now write it in polar, and this is 6, and the angle is 90 degrees. From here now, simplification is easy. 2 rules really, maybe more. But rule number 1, these are magnitudes. These are just numbers. So the numbers can easily divide. So if they're dividing, they'll divide. If they're multiplying, they'll multiply. So the V max or the I max, the number part, those can divide or multiply easily. Don't stress about them. So here, for example, you have 12 divided by 6, and that will give us 2. Now the next trouble part is going to be these, the angles. For the angles, treatment is more like exponential functions and the likes. By that, I mean when they are dividing like this, what do you do to them? Subtract them. So when they're dividing, subtract them. So in this case, this becomes the top part is 45. So this becomes the top part minus the bottom part. So this would be minus 90. And when you perform the subtraction here, we know to say this will give us negative 45 degrees. So this is what we end up with. So this is how you deal with these complex, with this polar algebra. Now, what I want you to understand here is, what if you had 12 and then you have 45 here? Yes, Daka?
I'm behind on how you took the 90 on top.
Okay, so here, what I was talking about here is, if you have VM1, and then I have this, and then let's say this is phi1 divided by VM2, and then you have phi2. The concept I was trying to sell here is, when you're dividing, these two terms are dividing. The first parts here are real numbers. These are just numbers. So for these two, they can directly divide. So if this is a 10 and this is a 5, it's 5 divided by 10. Directly divide them. No problem there. But the trick is with these two. So I can write this as VM1 divided by VM2. This is how you evaluate these two. And then you have our symbol here. Then we come to our angles here. But the concept with the angles is that if we are dividing them like this, then you have to subtract them. The one in the numerator minus the one down. So this is how you treat the angles. Have you got that, Daka?
Yes, I have.
Okay. But if you are multiplying, which is where I am heading now, if you are multiplying V1 and then we have phi1 here, and then you are multiplying this with VM2, and then we have this as phi2 here. If you're multiplying, the condition here is like this. Well, for the maximums here, again, these are direct, just multiply them. So this is going to become VM1 multiplying VM2. This is what you're going to get for the first part. But for the angles, now in this case, when you are multiplying, you add them. It's going to be the first angle plus the second angle. Have you got that?
Yes.
Yeah. So basically, this is how it works. So having gone through the phasor algebra, are we okay? Do we have any questions on phasor algebra, or we can move on? Go ahead.
How you tell that in this case you have to like
It's basically just algebra, really. You won't even have to guess whether you are dividing or you're subtracting. Look at this one, Ohm's law. Voltage is equals to IR. Let me start with time variable. IT is equals to, not IT, VT is equals to IT times the resistance. So this is what you have. And this perhaps is where we're going. So you'll see this very soon. But what if you ended up with this, but in phasor form? So that now you end up with this, but now this is the phasor current, and we have the resistance here. You see here, if let's say you are trying to get something for current, so that you end up with maybe I phasor is equals to, do I want to work with this one here? Yeah, but this is fine too, but let me just get the one for current, so that you end up with V phasor divided by R. But you know to say here, the next few concepts we're going to talk about here are going to be about impedance and admittance in the next few minutes. But from this description, we know to say this V phasor can obviously come in this form, V max, and then the phase angle this. But if the resistance here is not just our normal resistance, maybe it was actually coming from, even if it was just normal resistance, you have to see to say normal resistance, it means that it will only have a real part and no imaginary part. You should know also how to handle that one. But if this is actually impedance, not just resistance, meaning it's coming from an inductor or a capacitor, we know to say inductors or capacitor will most likely come with a complex value here. So it will mean that you have something with a J here, like we saw with a J6. Clearly, there's no debate here. You are dividing. Do you see that? Yeah. And if, let's say, you were instead just going for V phasor itself, not that, notice that now you'd have to multiply I phasor with the resistance, which is this. Again, I phasor here being a phasor current, it means that it can be written in terms of Im, and then with a phase angle like this. But the resistance, on the other hand, depending with what you're dealing with, if it's a normal resistor, which is what we use, like the normal ones, it will mean that it will only come with a real part, maybe 10 ohms or 5 ohms or something. This also just has a real part. Because it only has a real part, it should be possible for you to also present it in phasor form, as in you can find its max and you can also find its phase angle. And clearly, this is going to be a product instead of a division. But if what you have here, maybe you have an inductor or a capacitor, not a resistor, or maybe you even have both. If, let's say, you only have an inductor or a capacitor, it will now mean that what comes here will not be the normal resistor. Instead, it will be an inductor, not an inductor, impedance. And you know, impedance is going to have a complex form. So this is going to be a complex variable J, maybe with some variable, some number here, let's say B. Clearly, this is in rectangular form. This is in polar form. You are multiplying, obviously, but you'd have to first change this from rectangular to phasor polar. Do you see that?
Yes.
Yeah. So the algebra will be so clear that now you're multiplying, now you're dividing. Any questions? Okay, so let's now look at elements, circuit elements, but now viewed in for AC circuits. See, I'll keep it brief. Again, I'll avoid derivations, however tempting it might be to know. Now, as you saw, to answer some of your questions, I have even used Ohm's law, and I was able to present Ohm's law even for phasor form. But ideally, all we're saying is Ohm's law, this is time varying, is equals to current times resistance. If what you have is a current that is in form of a sinusoidal waveform, so that this can be written as the resistance, but the current is given in form of I max, and then you have cos omega t, maybe plus some phase angle phi here. Then you have to see that this current here the sinusoidal supply current here, it's possible for us to write it in phasor form. You see, throughout this is time varying. This is Vt. But the minute I choose to transform the current here from this sinusoidal waveform into phasor form, even the voltage I have on the left side changes. So the minute I say, okay, this is the resistance, but from this sinusoidal waveform, I decide to say, I will write that as I max and then the phase angle phi. Once I do that, notice that I have now represented the current in phasor form. And once I've done this, the voltage I have here is no longer the time varying voltage, but this is now the phasor voltage. So this is basically what we have here. Now, in doing so, this term here is actually the phasor current I. And this, of course, is to resistance, but now this is the phasor voltage that. Observe that this is Ohm's law, but the difference is instead of, I can actually rewrite this since we're used to IR, you can say the phasor voltage is equals to the phasor current multiplying the resistance. So observe that this is similar to your typical Ohm's law, V is equals to IR. But the difference is phasor voltage, phasor current, but basically the same thing that we do. Now, all I'm trying to move towards is to show you guys that the concepts of phasors is we're going to apply the same things that you guys have been using throughout, meaning it's mesh, it's noodle, and so on. But now we just want to say that, okay, the voltages, we can treat the voltages in terms of their phasor representation. Now, this is the expression that I was showing you here. This is if you're dealing with a resistor. This is the resistor that will come with a resistance R. So it's for a case where you have a circuit like this, and then we're supplying to a resistor. This is a resistor. We're supplying it a current I, and this current is in terms of a sinusoidal waveform, positive here and negative here with resistance R. But what if what you have instead is an inductor? If what you have is an inductor, again, I'll try to resist the temptation of doing the derivations, however nice they might sound to me. What if you have an inductor here? If this is an inductor, and this inductor is supplied with a current I, and this current I is in a sinusoidal waveform, well, it turns out, we can show this, we have showed it before, based on the fact that, one, the current source as a function of time, a sinusoidal waveform, will be given by I max, and then we have cos omega t plus phi here. From this state, and from the definition of an inductor of inductance L, the voltage across the inductor, V, is going to be given by V is equal to the inductance, then multiplying di dt. So what you'd have to do is differentiate this current source and perform the reductions as they come. Simplify the expressions as much as you can. In the end, you're going to end up with an expression for the phasor voltage across that inductor. And the phasor voltage is going to end up being V being equal to J omega, the inductance, multiplying the phasor current I. This is what you need to remember. Please remember this. You don't have to derive it every time. Knowing how it comes up is a plus, but for the most part, you won't have to derive that. You only have to know how to use it. But would you guys want me to show you how to do this? I think for those we interact with, I did show you guys how this comes up, but is there a need for me to still show you how it comes up from this up to here? Is there a need for that? Oh, we are okay. Are we okay with this? Okay, great. So from here, having done this, what I just want to point out here is, can you see this concept here? I have related Ohm's law to what we are doing, but look at this part here. Can you relate it to something? What quantity do you think this tends to kind of looks like? What is that? Okay, so okay. So this is what we get when we're dealing with an inductor. But what if we were dealing with a capacitor? But what I wanted to first just bring to your attention is this concept here. Sometimes you have to be able to read between the lines. Look at that term there. Compare it to Ohm's law, where you had V is equals to IR. Do you see what this term kind of looks like? Don't you see that it kind of takes the position or the place of the resistance R in Ohm's law? It kind of takes that because firstly, the place of voltage is taken by the phasor voltage. The place of current is taken by the phasor current. So this is fine. The only thing that is left is resistance R. And looks like this thing here does kind of represent the resistance. Well, it actually does. That is not necessarily the normal resistance R. Instead, that is the impedance. And this is taken as J omega L. This is the impedance coming from an inductor. Impedance, I can even define it here before we move on to a capacitor. Impedance is basically just resistance, but from an inductor or a capacitor. They do have similarities, a lot of similarities. And for starters, they even have the same units. Impedance is also measured in ohms, just like resistance. And when you have two inductors connected in series, we can add their impedance to get the total impedance by just saying impedance 1 plus impedance 2. And of course, it's the same thing for combining resistors in series. You guys remember that. And if you have inductors in parallel, again, the treatment is the same thing. You get the overall inductance, not the overall inductance, the overall impedance. Since they're in parallel, you can treat them as resistors in parallel. So basically, we use Z to mean impedance because this was the key difference here being that these are complex numbers. As you can see, it comes with a complex variable J. But other than them being complex, they are still basically just resistance. So this is what impedance is. So impedance is resistance, the resistance, but from a capacitor or an inductor, or anything really that gives you a complex value. In this case, these are the two that we're going to study. So if you're dealing with an inductor, this is what the impedance will be. But what if you're dealing with a capacitor? Well, for a capacitor, what you have is a circuit like this. But what you have here is we have our capacitor, and then this part is connected to positive, this to minus. And then this time around, our capacitor, we can still choose to supply it a current I, which is in sinusoidal waveform. We can even start with the time varying voltage across this supply. But the current flowing there, let's take it as I. Again here, we start with a voltage supply V in time varying equals to cos omega t plus phi. And observe that the voltage drop across a capacitor, if you guys recall, and not necessarily the voltage drop across a capacitor, the current that will be passing in a capacitor will take the shape of current I, time varying, will be equals to the capacitance, then dV dt. I think we looked at these expressions when we were looking at the LC and the RC and the RL circuits in some time back. So this is basically what you start with. And then by differentiating this expression and simplifying, you should see that you are going to end up with a form where you have the phasor current I being equal to J omega, the capacitance, multiplying the phasor voltage like this. But if we wanted to make it similar to Ohm's law, where you have voltage is equals to something, something current, then observe that you just have to divide this both sides, so that the phasor current now would end up being 1 over J omega C, and then you have the phasor current I. Now again, you have to observe that this term here takes the shape or the position. This is phasor current. This term here takes the position of resistance in Ohm's law. In other words, this would be the resistance of a capacitor, or since for a capacitor, resistance is basically also taken as impedance without the bar there. So this is going to be the impedance across that capacitor. So see the difference. When we're dealing with an inductor, impedance is just J omega L. That is what we had there. That is what we had. But if we're dealing with a capacitor, it's now 1 over J omega L. So this is the key difference between the two expressions. But when dealing with a capacitor, every now and then, you might have to move the J from the denominator and taking it up. Now, to do that, you have to recall that all you have to do here is multiply the top and the bottom by J, and also here by J. I think we did see this, so that in the end, it ends up the same expression, but with a minus. The J now ends up, but now you remain with omega L. Sorry, I'm putting L here. This is a capacitor. You guys should have seen that. Should have corrected me way earlier. This is for a capacitor, so it's not L, it is C. So my point is, through conjugating this term, we end up with these two, and these two expressions are basically the same thing. So depending with what expression you're trying to work with, you can start with this, but you might quickly have to write it in this form for you to perform some operations. Any questions? Okay, looks like we are okay. You see, if we look at the example that we did earlier on, which is this question, you see that if we actually wanted to transform this whole circuit, let's see how we're going to do this. So I don't want to go very far, so let me just, I'll use the upper space. So the first thing that we did earlier on was to transform the sources here into their phasor representation, which we did. So this ended up being like this. And then after that, even this one here. So I have this. Even this one here comes to be like this. Now, what you have to get here is that the frequency of the supply becomes the frequency of the whole circuit. And the best thing here is you have to see that in this question, of course, both supplies had the same frequency. This is 2, even here, by frequency, I mean the angular frequency. Even that side, it's 2. So the whole circuit will take an angular frequency of 2 Hz. Now, why am I emphasizing that? You see, this is a normal resistor, so we know how to work with it. But look at this one. This is an inductor. So if we wanted to find the resistance across that inductor, and of course, resistance across an inductor, remember we call it the impedance. So if I wanted to find the impedance across that inductor, for an inductor, the impedance is J omega, and then the inductance. So you can easily see that for a 2 Henry inductor, this is going to be J. The angular frequency, we get it from the supplies. And the supply is 2, angular frequency 2. Even this has an angular frequency of 2. So it's the same frequency. So this is just going to be 2 here. Multiplying the inductance. The inductance is 2. So I have 2 Henrys here. Clearly, we see this comes out as J4. This side, we have a capacitor. And for a capacitor, I'll say this is impedance 1. For that capacitor, I'll say this is impedance 2. Let's see what we get. For this capacitor, what we have is, we know how we get the impedance across a capacitor. It's 1 over, and then we have J omega, the capacitance. So this becomes 1 over J, the angular frequency, which is 2, the capacitance, which is 0.25. So from here, 2 by 0.25, what are we going to get there? So let's bring it here. It's 1 over, we have J, 2 by 0.25. So this becomes 1 over what? 0.5. And when we divide 0.5 into 1, we get what? We get 2. This is now 2 over J. But remember what we did earlier on? To take the J up, it just becomes negative. So this is now negative J with a 2 there. So I hope you guys remember how this came up. So that is our Z2. So our Z1 is this one, 4J. So we have Z2 minus J2, Z1 minus J4. So what are we now seeing for our circuit? Well, for our circuit, all we're now seeing is a resistor here, a normal resistor, and then we have an inductor here. Then we have a source here. And then we have another source here. And then we have a capacitor here. But once we have made the transformations, you see, when you look at the capacitor and the inductor, they might confuse you. But just view them as if they were just general resistors in your circuit. View these two. I'll replace these and just say, view them as if they were just resistors. I'll go a different color so that you see that these are actually not resistors. So view them as if they are resistors. But the resistance for this one is, this is the inductor. And for the inductor, we saw it's J4. And this one here, we see it is minus J2. So once you've done this now, to use mesh analysis, it's exactly what we did. View these as if they were just resistors. And use mesh analysis. Mesh current I1, mesh current I2. And then you have your mesh analysis all set up. So there you have it. It's done. Do you see that, guys? Just with what we have done, you guys are good enough to say we should be able to handle questions on AC up to, but before power. Do you see that? Because all we had to do is transform the supply into phasor form, this side and this side, change the inductors and the capacitors so that we get their impedance instead. And then there we have it. The impedance is as good as just resistance. The rest is now just using mesh analysis and then simplify the circuits correctly. Is that okay? Would you guys want to try this question out? Simply use mesh analysis to simplify this. I think we already converted the sources to phasor form. I think these are the values for the voltages. Can I let you guys try this one out and see if you can actually answer the whole question now, saying for the AC that use mesh analysis to find IO. IO is the current coming to pass through that capacitor. Would you want to use mesh analysis to find it? Of course, to find it, you have to see, since IO is the current coming this side, by mesh analysis, that current IO has to be equal to I1 is in the same direction with it. So it will be equal to mesh current I1, but minus mesh current I2. So if you can find the mesh currents I1 and I2, then this is what is going to give you your I/O. But just get one thing. What you're going to get here, it's not a value. You're not going to have an exact number to say I/O is 2 amps. You're going to have an expression for I/O. Okay. Any questions?